Yes, a well-known contrarian. Spend too much time on Facebook stirring up arguments as well as trying to solve them. I'll say at the outset I don't have the qualifications to be even talking about this in one sense, because I'm not a philosopher, I'm not an historian. I am, if you like, a STEM person, not a stem cell, but a science, technology, engineering, mathematics person. There's not a lot of it around in education nowadays, or what's left is very much watered down. It's just not respected anymore, or wanted, or needed, and no doubt we'll have robots doing it all for us in the future. But Adam and I have had long debates, arguments, fistfights about when will a computer ever become equal to a human being in thinking, that is academic intelligence, or in empathy, or in creativity, and such like. And we all hazard guesses at a possible future that might have such mechanical creatures, Frankenstein creatures. Ray Kurzweil has certain other opinions on it. I don't want to take any view on that at all, except to say that it inevitably will happen. Now that sounds outrageous. It sounds like a crystal ball prediction. What confidence can you have in that prediction, or in me making that prediction? Well, I hope that by the end of this today, you might have a little more confidence in some of the guesses that I hazard. First of all, we note that there are some people who allege, well, futurology. I call it futurologist, futurologisms, and all the rest, various names for it. But let's give a definition. Future studies are talking about possible, probable, and preferable futures. And since we've never had an artificial intelligence before, how can we attach any probability to the existence of such a thing? We can't. We can look at baby steps and look at their productivity, their likelihood, and where they'll end up in the end. Yes, there are huge hurdles along the way, I truly admit that. And we each identify the hurdles differently. And I don't wish to talk about the hurdles of AI in the future. I want to indulge myself. When Adam and I talked about this possibility here of futurism in the past, present, and future, which is a bit of an anti-chronology, if you like, I tend to fall into the role of the skeptic and say, what confidence can you attach to any of these predictions? Well, Adam challenged me and said, all right, talk about it. So here I am, and I'm going to give some indications of some things that we can be very, very confident about in the future, almost to 100%. And I'm going to take a long sideways step, and I'll probably dart off into a few alleyways, and if I go too far off course, just say, hey, what are you talking about? Get back on it, please. I have indulged myself. It was a long preparation for this, 2 weeks. It turned out to be about 11 odd pages, a little bit down the line. It's far too much for a talk. In tertiary education, one guesses that you can get through about 2 A4 pages per 1 hour lecture. That's at the higher levels. Lower levels, you might just flip things through and use PowerPoints and all the rest of it. 11 pages? No way. So to ease your minds and perhaps stop me sounding too boring, it's gone up on the web. Adam says it's up here somewhere. I'll go looking for it, I can't find it.
It's actually, you have a look at the schedule, there's a link to it.
Yep, in the schedule, he says. All right, we'll have a look to it.
At scifuture.org.
Yep.
I don't know why it's just done that, but yeah, you left it alone for too long. And there we go.
First thing I'd like to focus on is the people who say that the future can never be known with any degree of certainty. Of course, that's a self-contradiction because it predicts the future, doesn't it? And thank you, Mr. Epimenides, who thought of it first. He was a philosopher in the Aegean marketplace. So what can we definitely say about the future? Well, there's some things that apply not only to the future, but have applied in the past, apply to the present, and in the future. And I choose this thing, this mathematical thing. It's Newton's second law of motion. It's an equation. If some of you don't like maths and don't like equations, please be patient with me. What it says is that the force applied to an object of mass m will give acceleration a. Or you can turn it in the other way. If you know the acceleration and you know the mass, then you can find the force. Or you can turn it around a third way, that if you know the force and you find out the acceleration, then you can find the mass. So that equation, of course, has three variables. You can turn it around three ways. As long as you know two of them, you'll find the third. And that will predict what will happen to that mass now, or yesterday, today, and in the future. It's always true. Yes, there are experimental errors, plus or minus 2%, measurement errors, things like that. But as a general hypothesis, that's as reliable as you'll get. And we use it in engineering, in production of all of our machinery. We use it in biology, in pharmaceutics. That's the dog I've inherited, pardon her, folks. My daughter's gone over to Tasmania and she's left me with the dog. That happens, as my parents do. And I talk about these three things here. And if you want to pay more attention to that, you can by downloading the paper. Let's move on quickly and get on to something more interesting than goddamn maths, shall we? I assert that this law is frankly describing past, present and future, PPF, the state of affairs over 3,000 years. Why? Because it was first devised by Newton in 1687 and it's been true for this 1,500 years, and I'm going to rashly say it'll be true for the next 1,500 years. So there's something that's true for 3,000 years. Pretty good? You might say, oh, what about relativistic mechanics and what about quantum mechanics? Yes, there are alternative mechanisms.
You're overriding the basic question that equation defines force. And that there was no concept of force as a measurable thing in certain physical dimensions before Newton came. So you can't say it applied thousands of years ago.
No, I'm saying it applied from the date he conceived it. Yeah, in fact, all the errors that Galileo solved about acceleration, and they thought that bigger masses would fall with a faster velocity or a constant velocity, whatever. They weren't sure about it. Newton solved it in 1687. With the apple on the head, so to speak. So this is one example of a prediction of the past, present and future, which is good, which is valid for a goodly time. And I'm going to coin, Asimov had three laws of robotics. This is my first law of futurology. And there's a well-characterised, improved and trusted equation that will provide a good account of the past, present and future. How many of these equations are there about? Are they only in maths? Are they only in physics? No, they're everywhere. They work everywhere. They might even work in history for all I know, but I'm not a historian. A few disclaimers. I'm not saying that this first law of mine is an absolute truth. For if it were to be an absolute truth, it would have to be true for every observer in the universe for an infinite time. Though there may be variations on this in 4-dimensional space or 11-dimensional space. But if we take the caveat that this law, this one up here, works very well in our 4-dimensional space, that's x, y and z plus time, when we work in it every day, I'm going to say that that law will work for a long time further, and it's true not for all observers in the universe, because we can't interview them. It's not even true for all people on this planet, because it's very hard to interview them. In fact, even if you spoke to your family, you probably wouldn't find much congruence there either. It's very hard to get something that everyone will 100% agree with. But we can get a close approximation to that, and it might last for some time. So I'm going to assert that equations in maths, science, pharmaceutics, biology, and in philosophy, there are Gödel's laws belong to both mathematics and philosophy. Lasted for a long time. People have tried to disprove Gödel's 3 laws of inconsistency, if you like. Haven't been able to do it. It's got a good track record from about 1950. Added to these equations, there's a group in Melbourne called the Least Wrong Group. It's not just in Melbourne, it's worldwide. It's first set up by a chap called Eliza Yudkowsky. And if you like, he's a kind of like a Bayesian predictor. Bayesian statistics or Bayesian selection of hypotheses is a strange beast, a very powerful beast, and it had a stunning victory just a year ago when the Higgs boson was found. The existence of the Higgs boson was proved to the greatest percentage of authenticity ever before shown on this planet. I'll give you some figures shortly. But Yudkowsky is the guy who coined this least wrong hypothesis. And what you do is you get all the hypotheses that are contenders for predicting the outcome of some situation. You put them to serious testing, and you then give them a probability of truth, and go through a Bayesian sorting process. And you might find that of 10 hypotheses, there's only 2 that are up at about 0.9 or 0.95 or 0.85, and then you have the hard problem saying, where's the cut-off? Do we cut off everything below 0.8 or everything below 0.9? That's a different issue. But you'll find that there will usually be one at the very top which is the least wrong. It might be 0.95 or 95% authentic, but not 100%. The 95% is all we can go with, and let's rely on that. And so it's not this bugaboo that people talk about scientific absolutism. Nowadays, scientists tend to talk about Bayesian probabilities and whether it's least wrong or not. If it sounds too esoteric, and don't worry about the dog, if it sounds too esoteric, did you know that a large percentage of upmarket motor cars with automatic transmission have a Bayesian predictor in the gearbox for selecting your gears? It depends, it takes a track record of your driving history, whether you're a lead foot or not, whether you're going for economy or not, whether you're going up a hill or not, what gear it's already in, what gear it should go to in the next, and it uses Bayesian hypothesis selection for getting the next gear. There's a practical application in your car. There's also some microwave law. I can't say damn use of that. That's going over the top. Here's the Higgs boson, otherwise known as the Higgs God-mass particle. Most of us know of 1 sigma for a normal population includes 66% of the population. The Higgs boson was proven to 5 sigmas. And that translates to a 1 in 3.5 million chance of it being wrong. There's been no experiment in physics on the face of this planet ever before that has been that gold-plated accurate. Bloody fantastic, I say. And it set the standard and everyone has to live up to it now. Other accounts of the past, let's move on. I'm whipping through, I'm trying not to bore you. Certain traditional methods of accounting for the past, present and future are obsolete. Firstly, standard written history has fallen into considerable disrepute since most accounts are usually written at the virtual point of the sword held by the most recent conqueror, which only may be a winner of the new election. For example, Australia's 2014 Liberal National Party coalition has excised every instance of the Gonski Education Report from all public records. How's that for rewriting history, folks? It has stopped. Yes, on the left. Sorry. Terrible. It's not just ignoring the truth, it's deleting it. Another person who has, before we go on, the alternative to written history, by the way, and this is something I'm very fond of, it's a thing called forensic history. There's 6 DVDs of battlefield detectives. What they do is they go to locations of previous written history, dig them up, look at the artefacts and recheck them. And it was a stunning review of the Battle of Waterloo. Just go and have a look. They've rewritten history, written history, and they've provided their own forensic history for it. A much more accurate and faithful account. Another kind of forensic history is the ABC time team. It's not as rigorous as battlefield detectives. Previous futurologists, Arthur Clarke, his book Profiles of the Future. Originally 1962, you rewrote it in 1982. And this is his table of predictions for transportation, comms and information, materials manufacturing, biology and chemistry, and physics. Most of those entries are old hat because they were prior to this date or that date. And then he starts to hazard guesses for the future. In transportation, he talks about Earth probes, hypersonic transport. Actually, that was well beaten by the Concorde, wasn't it? Lunar settlements, the Japanese or the Indians are not likely to beat the Americans on that. Deep sea probes, passe now. Space colonies. Now, space colonies are not just colonies on planets or on moons. It's based on the idea by Eugene K. O'Neill, who in 1966 presented his idea to the Congressional Committee once, twice, thrice, 6 times he presented it to the US Parliament, Congress. And 6 times they knocked him back. Why? Because it was damnably expensive. Even though Eugene K. O'Neill said the rewards from having colonies in space, I'll define that shortly, will give you a payback period of 13 years. How? Well, the idea is that there's this funny thing in physics. It's called the two-body mass problem. If you have a mass m1 and a mass m2, and you stick them out in space with no other bodies around, so the only gravitational field is between m1 and m2, you give them an arbitrary velocity, pointing towards each other, or away from each other, or sideways. If the initial velocity is pointing towards each other, they will collide. If pointing away from each other, they will just disappear from each other. If they're a little bit different, they're just missing, they'll either go into elliptical orbit, or parabolic orbit, or hyperbolic orbit, and that means it goes up into space. You can solve that problem given the size of the 2 masses and the 2 velocities. You can solve it on paper. Bump it up to 3 masses in space. It's insoluble on paper. It can only be solved by computers nowadays, except for a smart fellow by the name of Lagrange. And in the old days, they used to offer prizes for these mathematical puzzles. Lagrange solved it by putting a restriction. He said that for the 3 masses, that mass 1 should be much less than mass 2, and mass 2 should be much less than mass 3, and he solved it for all possibilities of mass and velocities. Now, what would come to mind for these 3 masses? The first instance I'll give you is the Earth and the Moon. If you take the Earth there and the Moon there, there's a big difference in mass, and you take some other small mass in between, you can plonk it in between the Moon and the Earth, and at some point, it'll be the point of zero gravity. It will go neither to the Moon nor to the Earth. That's called Lagrange point 1. If you take a line from the middle of the Moon to the middle of the Earth, call that the baseline, and you construct an isosceles triangle on either side, 2 isosceles triangles, then at the vertex of these isosceles triangles, you will have what's called Lagrange point 4 and Lagrange point 5. If you put a mass there, as long as it's smaller than the Moon and the Earth, and it can be 1 mass or several masses, then as the Moon goes around the Earth, those masses are perfectly stable and will track the moon around. They're called Lagrangian stable points. There are two other Lagrangian points. There's one, if you take this point of neutral gravity in between the Earth and the Moon, you flip it around the other side of the Moon, that's called Lagrange point 2, it's unstable. There's another one, if you flip it round over the other side of the Earth, that's another Lagrange point, it's Lagrange point 3, it's also unstable. But Lagrange point 3 and 4 are perfectly stable. Another three-mass situation is the Sun, the Earth, and in between. And you can have Lagrange points 4 and 5 tracking the Earth as it orbits around the Sun. Any masses put at Lagrange point 4 and 5 will stay there, will not move. Perfectly stable. Are they being used? Yes, there are some satellites there, solar observatories. More importantly, there are satellites at Lagrange point 1 between the Sun and Earth. Hypothetically unstable, they've solved it. They use what is known as a halo orbit. So if you draw a line from the middle of the Earth to the middle of the Sun, put a mass at the neutral gravity point there, and then at right angles to that line, you rotate your masses in an ellipse or a Lissajous figure, figure 8 like the ABC logo, or any Lissajous figure, and it will stay there forever. And that's been used by the Sun, Earth, Solar Observatory. That's the satellites being used there. There's 8 satellites at Lagrange point 1 between Earth and the Sun already. Why am I banging on about this? At these Lagrange points 4 and 5, and there has been devised a group called the L5 Society in America. They want to put colonies in cylinders. What kinds of cylinders? Cylinders, at a first guess, 20 kilometres long, 10 kilometres diameter, rotating at 3 RPM, because then on the inside of that cylinder you have one Earth gravity. And then you put your farms, your animals, your humans on the inside of this cylinder. What do you do with the end? You harvest the sun by solar collectors and point it straight down the centre of the tube. How many people could you put on in this 20 kilometre long by 10 kilometre diameter cylinder? Roughly about 50 million. How many cylinders can you put at Lagrange point 4 and 5? Oh, about 1 billion. You'd easily accommodate all of planet Earth's population. This just diffuses altogether the population problem, doesn't it? Except for getting them out there. Is that what you're going to ask?
No, they'll breed up anyway.
Sorry?
Well, you can take as many of it as you want, they're going to breed up anyway, probably, so you can't solve the problem.
Oh, you need a policy issue. Add to this the policy issue that no new human beings are allowed to be bred on Earth. They have to be bred in the colony. How do we get them out there? I'll come to that shortly. But the ultimate end is that you have a small number of humans left on planet Earth who are called park rangers or Earth park rangers. Their job is to repair the Earth after we've stuffed it, and try and get it back to as good a condition as we can, and the rest will breed outside in these colonies. Now, how do we get them out there? And some people say, oh, the rockets, chemical pollution. Dead right. If you used rockets. Anyone heard of space elevators? Around Earth at present, there are certain satellites near the equatorial orbit that rotate at the same speed as the Earth, so they're above 1 point on the Earth. And the idea is you drop a very strong cable down, Kevlar, whatever. It's not been solved, I agree. Engineering has some development to be done. They have a space elevator competition once a year over in Arizona. The greatest height we've got to so far is 50 kilometres into the air. They only need to get to 100 kilometres and it's self-supporting. It'll stay up there, it won't come down. And the idea is, if you could connect from the stationary point on Earth to the stationary satellite up above, and you have 2 cables going down, one for an elevator going down, another for the elevator going up, the 2 of them would be in seesaw and use almost no energy and certainly no chemicals. Now, that's just one satellite above. What if you have another one? And another one, until you have a full ring around the Earth. And you can shunt all of the electricity harvested from the sun around this ring to power loss, because you're going to have some frictional losses, power these elevators going up and down to various points around the Earth. That's where you get to 100 kilometres above the Earth. And once you're 100 kilometres above the Earth, you are anywhere. When you've got to 100 kilometres above the Earth, the escape velocity is vanishingly small. It's under half a metre per second. You can go anywhere. Oh yeah, where do you want to go? Well, in fact, you don't even need rockets to go anywhere else. There are things called Lagrangian highways. Write it down, go and look it up, Google it. If you get on a Lagrangian highway, you can go to any planet in our planetary system for basically zero cost and energy in dollars. So get the space elevators going, get the people up to there, launch them off to the colonies, and if they want to go further and they want to colonise around our planetary system, they can do that. Well, it's not in Arthur Clarke's prediction because Eugene O'Neill came after this date when he first composed it. He should have paid attention to it by 1982, but Arthur Clarke didn't. The book, the Bible of space colonies that you should read is called The High Frontier, written by Eugene E.K. O'Neill it is. At the end, he gives the cost breakdown and he plots the dollars over time. At the front end of the graph, something like 13 gigadollars to begin with. Even the USA could not afford that, but a consortium of America, France, Russia, China could do it. Very expensive, and it's still true that in 13 years they will recover those costs completely and go on further and make profit. How? Well, first of all, with colonies in space, you've got zero gravity down the centre of this rotating cylinder, good for manufacturing gravity-free products. If you want to mine something, you go to the asteroid belt. Every element and ore that's needed by mankind is in the asteroid belt. Go and rip that apart. How do you get it from the asteroid belt to these colonies in space? You might have, some of the colonies might be factories, some of them might be dormitories, some of them might be research laboratories. You've got a billion of these to play with, right? So Eugene K. O'Neill's proposal was you have mass launches out of the asteroid belt, you carve up the asteroid belt, throw these mass launches back to the colonies. How do you capture them? He's got some idea like a baseball mitt. It captures it and goes round and round and round and slows it down. But there's electromagnetic launches and there's electromagnetic captures as well. Railguns, which will work. Costly? Yes. Payback? Still 13 years. Well, that's a space future. Sometimes when you get into futurology, you tend to get into the Dick Tracy area. Oh, what's the latest watch, the latest Samsung, phablet, all the rest of it. I won't get into that, except to point out something that's come true in the last 6 months. Q-spin revolution, which Patrick probably is on top of as well. Instead of storing our bits, our ones and our zeros in the computers electronically, and the transistor is either full on, all the current's passing through it, or full off, no current passing through it. That's not true. Transistors aren't perfect. When you turn them full on, they don't put through a maximum current. When you turn them full off, there's still a bit leaking through. So that's why computer circuits are costly because they create a lot of heat, and this is wasted electricity. Q-spin, you take electrons, and you get electrons to spin one way or the other. It's a permanent memory, just like a disk, and it's residing on one electron. How's that for density? The density's now gone up by a factor of about 10 to the 12. The heat's gone down by a factor of about 10 to the 12. How far away is it? They've got up to, with this thing, a 2-bit computer so far, or a 2-bit CPU. And what do we know about things starting with 2? 2, 4, 8, 16, 32, 64. It's inevitable that this will appear possibly within our lifetimes, definitely within the lifetime of our children. So that's something that was predicted back here, but with this word process. So that dot there should go to there, and it was invented round about here, 2013, 2014. There's prior work to it, but it's got out of the labs now, it's into development. The other thing I will point out is this thing called a magnetic monopole. This is quite shocking to me. It's almost like heresy. I've been in electrical engineering for nearly 40 odd years, and there are these things called Maxwell's equations. One of them is called Gauss's law, and when you integrate around a magnet, you get zero as a result. That is, if you have a bar magnet, you have a north on the top, south on the bottom, the magnetic lines go round, and you can put a big cylinder around it, there's none scoping out into space. You can only have a magnetic dipole, not a monopole, a single north or a single south. We thought it impossible. The bastards have gone and done it. It's very interesting. Just put the magnetic monopole into Google, have a play with it. We can adapt Gauss's law to accommodate this. For those of you in the maths, you know that integral of electric charge equals Q on epsilon, isn't it, Colin? Something like that. And there's a similar equation for Gauss's law. You've seen it?
Yeah, you can reach it.
Yep. So where once this thing troubled me, theoretically it doesn't anymore, and practically it doesn't anymore. What are you going to do with the damn things? We'll get Colin to speak to that on another occasion. There's a lot of Collins around, aren't there? There's me up in Ballarat, there's that one at Melbourne University, another at Melbourne University, there's two over in America. We're trying to organise the Collins take over the world. Right, this is the flawed table of predictions. He went through past predictions prior to his date of publication, and he spoke of them under the failure of nerve and the failure of imagination. It's a catastrophic record. Famous astronomers, chemists, physicians, politicians saying can never be done, like never heavier than air flight and so on. How can these people make such predictions without doing their bloody homework, I say? So saying, I'm going to be outrageous. I'm going to make two predictions for which I have no data, just great respect for the authors. And the first one is Edward Witten, and the second one is Juan Maldacena, or Chena, not sure. These two guys are reported in a book called The Hidden Reality by Brian Greene, who is not the same as Brian Cox. Brian Greene has written a fabulous book about possibilities for understanding the future, and that is not just 3D space, not just 4D space, not just 11-dimensional space, but multi-dimensional manifolds made out of membranes. Sound weird? Sound crazy? These guys, both Witten and Maldacena, have cracked two of the key theorems that needed to be proved, and that's in the last 4 or 5 years. What they say about Witten is that he's so good, he simply says something to be true, and then up to 100 years later, he'll be proven true. Better than that, everything he states sounds really radical, and almost every second year, results coming out confirming what Witten says. No, he's not a crystal ball seer, he's just a damn good mathematician. He started out as an architect, I think, and thought, oh, that seemed interesting, and he stunned the world. This guy, Maldacena, has solved the holographic principle for black holes. We thought we couldn't see inside a black hole. We can't get any probes inside there. Turns out you don't have to. According to Maldacena, all you have to do is go to the Schwarzschild radius outside of the black hole and observe the 2D information in that sphere, and you know everything about the hole inside. And he does some really crazy maths, because inside the black hole, they're not sure what's inside, whether it's 4D or 5D or 11D, but he says it all reduces down to a 2D projection on the Schwarzschild sphere. Has he been proven right? Just about. Just about. So these are two very interesting things for the future. Will it lead to space travel? Will it lead to Star Trek teleportation? Don't know. I'm not going to be silly and say something about that. Now here I go into my slamming time. Common tropes and trash. Science is always changing, you can't trust it. For example, people often say that relativity has led to an obsolete of Newton's laws. It's wrong, because Newton has a superb track record of description, design and prediction when it's applied to human-sized masses and velocities. Let's call that the Newtonian domain. It's a small domain. We know it every day. We bump into it with our cars and walking around. So Newton works very well there. Relativistic mechanics deals with huge masses like 10 times the sun and very fast things like above 0.8 speed of light. Do those two areas agree? No, they don't. In the Newtonian domain, Newton is right and wrong in the relativistic domain. In the relativistic domain, Einstein is right, and in the Newtonian domain, he makes no bloody difference because it's just too slow. But at the border where they meet, somewhere in between, like at about 0.4 of the speed of light and about 1/1,000,000th of the mass of the sun, they can conduct experiments, and when you use Newtonian mechanics, it predicts something. When you use relativistic mechanics, it predicts something, and the two are perfectly congruent to within vanishing points of error. So, Einstein has not displaced Newton. They are in agreement at the border. It's just to use Newton in one situation, Einstein in another situation. There's yet a third mechanics. It's called quantum mechanics. Everyone probably uses it. It's for very small things, highly energetic, things like strings. They're about the size of 10 to the negative 31 metres. And they contain enough energy, hypothetically, to breed our universe. Our universe, hypothetically, the Big Bang, was spawned by 1 or 2 strings. 10 to the negative 31 metres long, and enough energy to spawn our universe. You might think that's crazy. I'll give you crazy in a minute. I'll prove that actually the universe contains, I'll attempt to prove, the universe contains zero energy. And so it took nothing at all for these strings to actually produce the universe and the Big Bang. So Einstein didn't obsolete Newton. Quantum mechanics doesn't displace Newton. At the very small, you've got to use quantum mechanics. But at some region where quantum mechanics can apply and normal Newtonian mechanics can apply, and they're either side of that border, the two are perfectly congruent to within vanishing errors. So all three of them can, all the domains of application can work in parallel at the same time with no fear of contradiction. I'll put in a little plug here, sorry folks. Still some may say you've got to be fair and teach all the theories and not just the scientific ones. And I say, okay, if I agree with that, I should teach the theory of gravity and what's the other one?
Divine command.
Sometimes Yudkowsky's even wrong. There are some theories that are 100% true. There's never been a counterfactual ever. I'll give you one. By the time I've been standing up here and blabbering, I have never used a word containing 25 Z's. There's an absolute truth. It's in language, it's in philosophy of language, true, but there are other things in recordable history. It has never been contradicted. For example, the stone's form. People may imagine that it levitated, but no one has ever seen a stone naturally leap up from the floor and go up into the sky, even though quantum mechanics predicts that it's possible. But to such small probabilities, we'd have to live a long time to see one happen. See, things are vibrating. Statistical theory, kinematics and heat. And sometimes all those things might vibrate in the one same direction. Boom, the stone will go up in the air. We've never seen it, because usually all the atoms are vibrating in different directions, not uniformly in the one direction. All this is very scientific, leaves no room for human qualities like love, spirit, empathy, etc. This is where I put on my Frankenstein mask and start snarling at people. If I don't do that already. My answer is Schlegel. WTF is a Schlegel. Everyone knows what WTF means. You may rhetorically ask, and yes indeed, so I'm going to get a bit wild here. I'm going to postulate that on your shoulders, everyone here, there is a Schlegel. It's not detectable with human senses. It's not even detectable by a proxy scientific device. It exists only as a word that I've just conjured up. And this word is detectable to you only by your ears, and if we were to write it down, by your eyes. Does that mean a Schlegel exists? Well, what we then have to turn to is what is called meta-language. Instead of talking about the Schlegel, we talk about the properties of the Schlegel, the meta-language. And then you've got to say, well, you can talk about the properties of something that's non-existent. Does that mean it exists? Not necessarily so. It's the word exist is the puzzle, is the problem. The answer depends on what we exactly mean by the word exist. If existence means sensate detection, no, we can't detect the Schlegel. If existence requires a clear definition of this word Schlegel, no, I haven't defined it to you, have I? It's just a nonsense word so far. It's a meta word. It may have been invented by some witch doctor. No doubt Schlegels have never existed for you before until you used it. Your first and proper view is that the user, me, before you, is on some strange medication or narcotic, or has a long history of mental illness. And that's a proper response. This guy's talking about Schlegels. You can't define them, can't touch them, you don't know whether they are, he hasn't got a meta definition of them. What the hell are they? Well, can we solve it at all? No. It's a semantic problem. Philosophy of language has a slot in it called semantics, and that didn't solve it properly either. I think we just got to use common sense. If you can't detect it with your own human senses or with any proxy scientific device, it doesn't exist. Yes, there may be things out there yet to meet, but now we're into future predictions. Oh, there will always be something in the future that you can't detect. It may very well be so, but as we know of now, there's nothing that we can't properly detect. And only Wednesday this week, dark matter. The big problem, dark matter and dark energy, we don't know what it is. Go look up the ARXIV physics records. They've now solved the problem of dark energy. Mostly solved it. This is a great breakthrough. Most of the mass of the universe we can't account for, but 80% of the mass, is it? Anyone know? 80%? 70? Solved, folks. Go look up Arctic. Where do we go from here? Oh, what is love? Well, the best answer is go and see the movie Love Actually. Absolutely charming movie, was it not?
Yeah.
Laid back, humorous, didn't offer anybody answers, and I don't think I will try to offer any answers either. Except this guy, who is it? Well, go and have a look at it. He says that all people suffering from love should be medicated. Take that as you wish. My CK solution to this endemic language illness, we all suffer from it, whether we're in everyday language or physics language or maths language or in whatever. My solution is we're all adrift in an unreliable philosophical lifeboat constructed of very flimsy words on a chaotic sea of poor definitions. Therefore, folks, cling on to whatever words you can agreeably share with your near and dear. Enjoy your own Schlegels together with a wee up and a lot of music, some crazy dancing, and a reliable stem. There's my prejudices. That's the best I can offer. You can take any word in our English language or any other language and you can analyse it, all meaning out of it if you work on it.
Are you referring to STEM, the John Smart version?
I'll let John Smart till later. It comes up. Thanks for the tip about John Smart too. Everyone likes non sequitur? Can you read it or not? Well, it says here, apples and oranges. What is that supposed to mean? You think I'm some kind of fruit. It's bad, isn't it? This one says, wait, you as in you people, eh? This one says, oh, I get it. About how fat I am. And this one says, you're anti-vegan again, are you? And this is called the first and last group of the easily offended. Doesn't matter what you say in any society, no matter they have all meaning, there are some people who are not only offended, they insist on being offended. I have no solution to that. CP Snow, this is highly provocative, so I'm going to skip over it. You can read it on the net.
Just a note, we're into lunchtime now. Feel free if anybody needs to go and grab lunch, but we can continue to move forward with Colin's talk during the lunch break. But you know, if you feel like eating,
This would be
feel
a
free
good
to walk
spot to
out.
stop if you wanted to stop folks and go and have some lunch. Yes?
Well, I mean, it's up to. I think for people who want to see you finish the talk, I think it's
I
still
was going to
worth
go
doing.
on a bit, to just another half a page if I may, and then I'll stop. And there's so much more. What I would like to do is just scroll through and say, do you want to talk about that? Or you want to talk about that? Or do we want to move
We've
on?
actually got something else at 2 o'clock, haven't we?
Yeah.
Yeah.
Lunch would be a good idea, wouldn't it? Let's take a break. Sorry, up the back.
You can't up the viewing slides after I've left.
Andrew, where is he?
No.
No.
I mean, we had somebody working on that for about 15 minutes before the talk.
Yes, it's. I think the group ought to buy a decent projector and a Mac machine, yes, and a Windows machine too.
Yeah, it'd be good to have all the resources to buy everything and have all the
Let's go
have
for
the
lunch,
money
buddy.
for a good.
Thank you for your
location.
patience so far.
Thanks, Colin.